Banana, 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 So, today we're going to be deriving or explaining how something came about. And that something might show on the screen. I don't know if I'm going to edit that in later. But it basically is going to be position formulas for weird transformations with a few assumptions that we're going to make. And this is something that happened during, early 1900s, well, really since all time. But first we're going to go over a little of a simpler explanation to start us off, or not explanation, simpler scenario to start us off. It's a bit of a relatable one too. So I'm a child on a playground, right? I get off the slide, I slide down. There's an older man, maybe, I think this is going to be you in this scenario, a 40-year-old man, sitting on a bench, and he sees me get off the slide, and he's like, I want to play with this kid as well. So he starts running after him. Well, this is going to be in his rest frame, so your rest frame. So you can think of this in two different ways. So this is going to be in your rest frame. So to you, you're not actually going to be moving like relative to yourself. Instead, everything else is going to be moving at a speed. So your motion is going to affect basically the motion that you see everyone else. The train is, instead of you moving back and the train moving forward, you're staying the same, the train is moving faster. So, to you, I move at some speed. I, the child, am running away, because I don't feel very comfortable. Speed you, alright? It's good to know. And let's say I'm a little bit of an idiot. So I trip on a little rock right here on this plane. Well, actually, before I say anything else, so I wrote two different ways because there's different. This second dimension is actually useless here, so you could just do the same thing, and I could be tripping over here in one dimension because this is basically one dimension, but you can basically apply it to it just be the same way, just the same thing. But I think most people are used to saying Cartesian coordinates like that. So, okay, so I'm moving speed u. Here is basically your origin, and here is my origin. This is where I started off. I got off the slide at this point here, and you started at the bench at this point here. So here, there's a distance ut. So the distance from my frame to your frame will always be essentially changing at a distance of ut, where t, of course, is the time elapsed during this whole interaction. But I, relative to my own frame, am moving, because this is in the rest frame of you, not the rest frame of me. So I will be moving at a distance that we're going to call x, right? So this is the distance from origin of my reference frame to the place where I tripped. And so you're going to see this at a distance of, maybe I shouldn't do it in that color. You're going to see this at a distance of, we're going to call it x prime. And so my question to you now is, how am I going to relate all three of these? Because they have an inherent relationship with each other. It's a trio. It's a very exciting relationship. And we're about to draw out a very graphic threesome here. And so let's go ahead and write that out. So, maybe I shouldn't do another line. Oh my god. So, here's threesome. For you, here's what the threesome is gonna look like to you. To you, it's just a combination. It's these two having at it. It's these two right here. So it's the patient distance I see from my origin to where I tripped. Like looking back, and I saw the place behind me. I'm like, wow, I'm this far from it, right? Plus the distances between our frames, me and you. Okay. And now we can use this to find how I would see it, like how I would see it, right? Okay. So really, you can just do the algebra if you want, but it is a subtraction of the distances between our frames and this distance that you see from the position that I tripped, right? Think of it, it's just a combination of these two. They're parallel with x prime, so it makes sense that the combination is right. But that doesn't really matter, because that's not the big expose of this video. It's not these are here, but we're going to use these. It's going to be a big part of it. Basically, all I wanted you to see is that there's a relationship between all these values here, and that's always a nice thing to have. But now I'm going to suppose something similar, but it's going to have some consequences that are, like, it's going to seem like normal, but in reality, it's pretty weird. So I'm going to do this, and I'm still the child, and I'm an energetic child, so I like to bounce around things. I like to go up and down and do all sorts of random things. So I bounce up to the top from the bottom, like so. Oh, and this is how an observer sitting on a bench. It's not you. It's not the one that's going crazy. It's just some other dude just sitting. He's mesmerized by my motion, and he decided to sit down and smoke a cigar or something. And you are always in motion for some reason. That's not supposed to look like a word. You, for some reason, are always in motion, and so you run along, and you run both by the sitting bench person and by me, who is in motion. And so basically what that's going to look like, right, is you're here, and you're moving at speed. Once again, we're going to call it u, but this time it's your speed. So, right, we have speed of u plus the speed at which you see me going. And so the question is, what is the speed going to look like? What is my motion going to look like to you, right? So this is really position graph per se. It's not like adding velocity, it's adding position. But actually, you could do either. It doesn't actually matter. Anyway, with the addition of them, it of course would look like this. And so my motion in your like if we change this to now being your rest frame, it would instead look like my motion would be such, right? In that area we had before. You're moving this more of a triangular motion. The thing I want to tell you first is that in both of these scenarios, well, I guess with the same scenario from a different perspective. So I'm just getting my markers. I should probably put them on my ear again. Is that I'm really kind of a weird guy, so I decide that I want to run the same speed in both scenarios, right? There may be different directions, whatever, but I'm moving the same speed. Okay, stop right there. Stop right there. All right. What you meant to say, yeah, you. What you meant to say is that both observers agree that I'm moving the same speed, because that's a really clear distinction to make. Yeah, that's what I meant. I should use blue. Alright. So I'm moving at, we're going to call it speed c because I see you, you see me, we see each other. It's always good. Speed c, speed c, speed c. Always the same speed. Now, can you say the same velocity? Maybe not, because different directions, right? Basically, what the weird thing I'm getting at here is, if you notice, it seems like a very common scenario. But the odd part is, this distance here is not the same as this distance here. This distance, I think we all know, is greater than the distance parallel, because these are both the same height. Maybe I didn't draw them right. It's the same height, L, here, right? So if I'm going the same speed in both, but traveling a different distance, wait a second. The observer here that's sitting still watching me go up and down, or whatever however you want to think of it, right? is going to notice that I hit the top before I hit the top in this scenario where you're moving forward, even though it's your rest frame. This motion looks like that, right? So you're gonna observe that I hit. If these two were to have a conversation between each other, like they're gonna talk, he'd say, and they had, like, let's say I have instantaneous, like, communication here. He's like, hey, this kid hit the top. And you'd be like, no, he didn't. He did not hit the top yet. What are you talking about? You're crazy. You're insane. And so now they want to have, like, some sort of way to agree with each other. And so we're going to come back to what we used earlier. I should have added a space. And they're going to say, so obviously this won't work anymore. So I want to propose some sort of sanity in this world to where there is a relationship between these two here, but I want them to change by the same factor. I want there to be some sort of sanity such that we change by the exact same factor here. And we're going to call this factor gamma. The naming doesn't matter as long as we understand that we're both changing by the same factor, gamma. Right? So we want these to change such that it may not be the same distance, but it can at least change by the same factor, gamma. And so what we're going to try to find first is what this factor is under all of this. So I think the picture should hopefully be clear here, so I'm going to erase it to have more space. Start that again. I'm going to go under something. In the previous scenario, there was something kind of hidden that we assumed. And here it is. We assumed that we would both agree on the time. Now, I don't think there's anyone in this world previous to the 1900s would be like, yeah, I tripped in 5 seconds. The guy behind me didn't think I tripped in 5 seconds. that would propose a lot of weird scenarios, right? It's like, time travel? What? What's going on here? No. Well, whether that you think it's that or not, this is the assumption that was just kind of hidden in our previous scenario. The first scenario we did is that in both frames they'd agree on the time, right? Well, just because I'm a lunatic, we're gonna say that they're not the time, and that all that's really gonna change here is that this. Remember, this is x. This is gonna be the prime time, because if we left this on in the as the same t as up here, it'd be we're basically saying that the t prime equals t. If we were to say that this is t, in finding the unprimed x, right? But now we're saying this is a separate quantity, or we're gonna say that it is, and we'll see whether that's true or not. Okay, so something to see also from the previous scenario, we did this, right? I think if you know your basic trig, or just basic physics, right? We're moving at a speed c and time t, so that's going to give us our distance. And so for this, it's going to give us our unprimed distance because we're using our unprimed time. The speed is going to be the same for both, so it's not going to matter. And so our c, t prime would then be our primed position of the other one. So that's important to note, so I'm going to kind of write it up here. And something I first tried was, you could set ct prime with x prime equal to this. So it could be like c prime equals alpha x plus ut. But that doesn't really help as much because it it's in terms of a lot of things we don't necessarily know. Because then if we were to solve for gamma here, it'd be gamma equals x plus ut over ct prime, right? And we don't necessarily know the relationship between the unprimed and the primed time. So you could try it like that, but it's not really going to get you anywhere. But it's good to try weird stuff. Yeah. So instead we're going to do a little bit of a weird thing, and we're going to multiply these two that we found and see if anything juicy comes out of it. So we're just going to do x plus u t. So nothing really crazy. What we're going to find is that we're going to be able to basically cancel some stuff out here and really simplify this down to solve for something for this in a meaningful way. Okay? Something we should do first. Okay, so the reason we found it in terms of these is so that we could substitute in for these x. That's the other thing with the other method I tried, is that it was in terms of something we didn't know, which was the distances. Because the distance had the definition of alpha in it, so we have to use something that doesn't. Right? So something we're going to do first is we're going to, of course, substitute these in, so this would become then, and you could first expand this, but I find it simpler to first substitute. Yeah. And I'll show you why, of course. I'd be kind of an idiot to not show you why. So the reason is because both of these terms have a common factor of their respective time in them, so they can factor it out here, which would then be able to cancel with this. So t, I'm sorry if that looks like a delta, it's not supposed to be a delta. And then it would be c plus u, c minus u, and this leads to a much simpler expansion of that. It would just be the square, the first minus the square, the second. But first, we're going to factor this out, this t times t prime out. From both, right? So that we get and then expand and from here we can just simply solve for our gamma. I always say alpha, I always say gamma. You call it Lorentz factor, which shouldn't exist right now because we're driving it. So we should think in the minds of we don't know what Lorentz is. Anyway, you just solve for that. One method you could do squared and then expand. I hope I have space. Yeah. Anyway, I'm just gonna solve it. You can always do this as an exercise. That is really small and kind of sad that the small thing is what we tried to find. So I should probably erase this all. I'll leave it there for a second. Basically, this is what we found. And that's what we need to find. Because that is exactly the question that I asked. Cool. And I'll show you some really nice things what we just found. So what we found is this factor here. And we found it to be this. And the really nice thing is we found this factor only in terms of of the relative speed. So if you were to think of yourself moving at speed u, that's all it is. Like you're running past a person at the bench, or you could think of it as the horizontal speed, like horizontal component of my speed if it's in your rest frame. But either way, yeah, it's only in terms of like natural numbers and this constant here, which is my speed, which is all the same for all observers, right? And then your speed. So it's really nice that it's only in terms of those and nothing else. And so we could also rewrite our previous ones like this. They're going to be equivalent, but I'll show you what they look like. Looks like that. It's the same thing. And sure, I'll go ahead and show you. You should need to make sure to remember that this is in the other frames, the primed frames time variable. But they're both going to be changed by the same factor. That's the entire assumption that I gave you, that I made. Right? And so now something to look at is the property, not maybe like the limits. What's the domain of this factor that we just found? Like, what values can it hold? And what are its limits? Well, being a fraction, of course, and using standard mathematical intuition, right? We all probably know that this cannot be zero. This denominator here cannot be zero. OMG. And so, just out of curiosity, what must occur for this to become zero? So what can this not be? Just by looking at this expression, what would happen if this were zero, and what would be true? So we do know that this c is not equal to zero, right? And if for this to be 0, you can simply, in order for this then to be equal to 1, this factor must be equal to 1, and in order for that to be true, or actually should really be u must be equal to c. So the weird thing here that we just found from this expression, if this expression, or if this equation is true, is that your speed cannot, the speed that I say mine always is. So if we go back to our scenario of, we're just going to go back to this one, where you're moving, let's say you're moving at speed u, I'm moving at speed c. We're saying this u cannot be equivalent to this speed here, which is kind of weird that there's a natural limit to the speed that you can even travel. That's just based on this, whether or not how accurate that is, because there's a little weird thing where if I were to go above, okay, here's the other thing. We'd have to write this in terms, in using imaginary numbers, using I, if my speed were to be greater than yours, right? So we'd have to use I if u is greater than c. And so here comes the natural, or the typical phrase where you can't go faster than something. And I'm trying to stay away from this, from my speed, because I want this to be my speed. So we all know you can't go faster than me, right? No one is faster than me, man. All right? I'm telling you, because otherwise, this whole this whole factor would have to be imaginary, which would be kind of a weird factor to have in. I don't exactly know how you would even use it at that point. But, so we found a few things here. We're just going to say that they're true because, why not? So we found that I'm going to put not greater than c. Oh wow. No, we could just say u is less than c, and u does not equal c. However, this is just the speed of that observer that's moving. And now let's observe the situation, or let's find a parallel from the Galilean world, where it's the first scenario we did, where everything is very typical, to this one right now. So I'm just going to quickly redraw this scenario where should probably use the right marker. Where I'm moving up and down. Yeah, also moving like this. But this time you decided to stop moving, so we're both actually. Oh my God, it's in the back. And yet I stop. So we both look the same here. Now if I ask the question, if these two were to have a conversation between each other, they would now agree on the time. So now in this scenario, which is identical to the Galilean transformation, which we did before, and where we said this is an inherent assumption. This is something that is just hidden in our Galilean transformation. And so basically, if we're going to say if your speed is 0, then we agree on the time. We may not necessarily agree on the position because you could be a little bit, like your bench could be at a different position than mine. We could basically like be moving. We could be inertial observers, right? So moving, our frames could be moving relative to each other, just not accelerating moving relative to each other. So that's a cool thing. It's kind of like the parallel between the Galilean and the non-Galilean transformations is in this one specific case where you are not moving relative to me. And that's because it's the identical kind of motion. Not exactly identical, but yeah. And so now we're going to find, so we found what it can't be, but let's find what it can be. So basically, we found that 0 equals that. So what does this, you could probably think of this logically, very simply. What must this be when our speed is equal to 0? Or in order for this to be Galilean, what is this factor must be? Well, Galilean, in order for it to be Galilean, this factor must be equal to 1, because then we'd have equivalent, right? If I were to cover this up, we'd have an equivalent transformation to before. So we have is equal to 1. Right, gal. I don't like gals. Yep. And so now if we were to find the limit as this approaches C, because we know it can't be C, but as it approaches C, we can use some nice limits. This is a good point. I'm not going to go through like the rigor of, oh my. But basically you could find the pattern, like what occurs. All it's going to say is that increases. It doesn't necessarily have a maximum. It has maybe a maximum for a certain value, but it doesn't have a maximum in general. So what we found is that alpha is a value which is greater than or equal to 1. So we can equal 1, and if it equals 1, Galilean transformation, essentially. But this is a way, we basically did another transformation in order to get to the transformation of the Galilean to these Lorentz, which is what we derived here. I'm not going to go into solving for time, because you can, of course, do this instead of just position. Because I stick in the original scenario with position, I'm going to stick with position in the second scenario here. But basically, we just found the domain of this. Thanks for making it this far. Here's just a quick conclusion on what we did. So first, we of course derived the Lorentz factor. Well, we derived these simply just by me saying it like, oh, let's assume this, let's assume that. And then from these and a few manipulations, we found the Lorentz factor in terms of the relative speed and a constant here. We didn't really touch on solving for time in these, but I think we're going to get to that in the next video here, which will include, of course, time dilation, limit contraction, and a muon example problem. These basically are properties, or like consequences of what all this says, and like the limits of this. We'll do some other examples, but should be all for now, and I'm going to consume you, and then I'll spit you back out for the next video.